This is the Telecoms Academy NFV SDN Insight webinar. My name is Murray Cooke. I am going to talk about three things in this session this afternoon. We want to highlight what's happening with the key SDN and NFV initiatives. I'll explain those to you. While we're doing that, I'll explain what the leading use cases are, what people are actually using this thing for, and we'll summarize at the end with the expected business benefits. I'm Murray Cooke. This is a quick sort of potted history of my experience, some relevant experience. I was in British Telecom and head of operational engineering at BT Global Services at the back end of the last century, looking at how we build and operate managed services, and then moved into a unit that was looking in the group CTO's office that was looking at software-defined networking. And when I left BT in 2008, I moved over to Intel, and I've been the solutions architect looking at major operator developments across Europe, Middle East, and Africa. And I've been involved in NFV standards launch and also working with the ecosystem that's around us. Is the equipment vendors, the software vendors, the integrators, consultants, and standards people. So that's me. So the key initiatives and use cases. Firstly, I'm not sure how many people have seen this sort of picture before. This is the sort of classic SDN architecture picture that we get, where we get data traffic going through the data plane, typically through a switching fabric, and how that switching fabric forwards traffic depends on routing tables that are set up in it. And we have a thing called a control plane that sits above this, and this has got the rules about what data should be routed to where, which path should it take next from the switch. And there's various protocols and things that are associated with this. And in the SDN case, the key protocol on that connection on this link down here between the data plane and the control plane, this is typically where we get open flow. North of the control plane, there's a wide range of things happening up there, but up in the management plane, we have, if you like, the higher level strategic view of what's going on. What's happening in the network, what sort of traffic have we got, what do we need to change, what rules are we going to send down to the control plane to modify the way things work. So this is the classic sort of architecture. However, SDN is now being applied in four main areas. Historically, it was set up originally to look at the evolution of routing protocols for IP networks by some researchers in the States, but very quickly people said, aha, this is what we want for data center local area networks to replace the sort of spanning tree approaches that have been historically used on local area networks. And this was to enable massive scalability of data center lands. If you wanted to connect thousands or tens of thousands of servers onto a network, you needed something a bit better than spanning tree. You needed to be able to control things far more in a fine-grained way. And so that's, if you like, one of the main application areas for SDN. We've also got a thing called transport SDN, which is the equivalent for wide area networks used by telcos, typically the optical networks that they have, CWDM, DWDM, wavelength division multiplexing sort of networks, and this is all about exploiting the bandwidth in those networks on the fibers between the network nodes in the most effective way. So things like changing the use of the bandwidth on a time of day basis. Overnight you might want to use the pipes for disk file backup, for example, between a couple of data centers, and during the day you might want to run branch networks or something like that on them. There's also a thing called a software-defined WAN, which is a recent development which is used in enterprise networks. And what we have here is what you could call an edge approach, where enterprises are interested in exploiting the available bandwidth that they have to the best effect to operate their applications. So if, for example, you've got some, say, customer service traffic, people using an order entry system, and voice over IP and email, you might want to prioritize the voice over IP traffic to get the best performance so that there weren't any voice hits. Similarly, you might want to make sure that there weren't any outages on the main order handling system. And if the email got a bit delayed, did anybody really worry about that? And so configuring the boxes that go at the edge of a classic sort of IP network, a broadband network, you can do that using software-defined networking techniques. Another area that's emerging is called network service headers, NSH, which is used for a thing called service chaining. And if you consider, for example, how a mobile wireless network works, there's a bit in the back end of a mobile wireless network where the wireless network stops and it plugs into the internet. And we're going to want to have a firewall there for a start. We might want to have DDoS protection. And then we might want to have various sorts of different filters or processors. For example, for video traffic, we might want to have a content distribution node. For email, we might want to have a spam filter. For web traffic, we might want to have a parental control filter to stop porn being distributed. And what we have is the ability to set up service chains. So all the traffic might want to go through a firewall, but only the video traffic goes through the CDN system. And what we get here is the ability to set up service niches for individual user groups. And this is starting to get very interesting as we move towards 5G networks and putting lots of different applications on the network at the same time. How are the requirements for assisted driving, augmented reality, and machine-to-machine traffic going to be handled alongside the classic applications? Okay. So what's happening in the SDN space? One of the an interesting development is this thing called ONOS, the Open Network Operating System Architecture, and this is taking that controller layer and making it hugely scalable with a distributed core, so that you can build massive networks under a single control domain. And also it has a northbound application intent framework interface. And what we get here is the ability for an application to say, I'd like some connectivity between here and there, please, in the network. And all this lot sorts out what that means. And what we have at the bottom could be a series of data center LAN switches like in this picture, or it could actually be all the previous stuff that we saw on the previous slide, all joined together to give you an end-to-end service approach. So ONOS is an interesting project if you're looking to find out what the state of the art is in here. Good thing to look at, ONOS. This is the software-defined WAN that we were talking about. What you get here is this approach with a centralized controller. And typically, what people want to turn on at the edge of the network is, for example, a firewall. So if this IP network is, say, the internet, if I'm going to connect my enterprise branches to a data center, I want to make sure that I don't get interrupted by rubbish coming in from the internet. So I want a firewall in there at a minimum. I also probably want to secure the traffic across the public IP network. So I might want to have a virtual private network tunnel terminator, IPsec or SSL, these sort of applications to make sure that people can't intercept our data and understand what's going on. And also this requirement for quality of service, setting up what sort of traffic is going to get priority, what's the bandwidth that you're going to allow for individual applications. So you're tracking application flows as they come into the edge of the network and making sure that they've got an appropriate amount of bandwidth, and that so that we get the right end-to-end service performance. This sort of technology took off very strongly in the States, probably about 18 months ago. And there's companies like Viptela, recently acquired by Cisco, who've been doing a lot of things. But there's a number of companies in this space. One of the features of this lot is that we have a centralized controller capability Typically, that could be provided either by the telecoms operator of the IP network, or alternatively, the enterprise can have their own one, and they can have complete control about how they best use the bandwidth that's available on the IP network. So that's in a nutshell what we have with software-defined WAN, and this is equivalent to what we might have seen in an enterprise network using multi-protocol label switching, MPLS, but at greatly cost reduced because we can use commodity broadband network services instead. Okay, so this is the NSH stuff. And what we get in here is the network service header. So when some traffic comes into the edge of the network here, it goes into a classifier, and so the payload say, okay, right, what kind of flow is this? If it detects it's a video flow, for example, that flow might need to go through a firewall, a cache, and say a video accelerator. So the traffic goes off into a network, typically a LAN, and goes to the firewall application, then to the cache application, then to the accelerator application before it pops out the other end. And what this gives you is the ability to very quickly route traffic amongst applications on a network. And the SDN controller that we see here has the ability to set up the classification rules very quickly. And so this is how we can set up new market opportunities or try things out, or even operationally to divert traffic to backup data centers and things very quickly. And the beauty of this is that because it's all done up at the sort of IP networks and higher, what you can do is you can be completely independent of the network. You don't need to reconfigure the network. The network's just set up as a local area network where the traffic is distributed to all the hosts, and the hosts pick up the data that's of interest to them by looking at the headers on the payloads. So when the payload comes in, if it's video, it says FCA, and the F application, the firewall says, that's for me. I'll process it and send the output back onto the network with just the C and A headers left on it, so that it goes to the C application, then the A application, then the payload pops out the other end. And there's various technology like proxies available, so that you can interface simple applications onto this stuff. Okay, so that's roughly where we are with SDN. Where are we with NFV? So the NFV story is about the evolution of classic telecoms equipment devices. And classic devices are typically built by equipment manufacturers who will create a network function that runs on a dedicated single function appliance. Optimized, tuned to handle telco levels of bandwidth. And what's happened over the years is that commercially off-the-shelf or COTS computers are now have been developed over the last 10 years with vastly improved processing performance, so that typically on something like a standard 2-socket server, you could quite happily process about 10 gigabits of data in a single commodity server. And so what's happened is there has been an evolution from the fixed function appliance to the same software but running on a commercial off-the-shelf server. And this has been very popular in areas typically like call control servers, internet multimedia subsystems, and mobile networks. And that was the next stage. Okay. So moving on from that sort of approach, people then started to understand the opportunity presented by virtualization. And this uses techniques like hypervisors so that the underlying server can be shared between multiple applications simultaneously. So what this means is that the operator, instead of saying, okay, I need a server for the production workload and I need another one for the backup workload, even if the production workload is only consuming, say, 5% of the server, you still had to devote a complete backup machine for this. When you got it virtualized, you can put multiple workloads onto one server and get up to a commercially effective grade of utilization of the server, say 20%, say 90%, that sort of thing. Then moving from there, we get into orchestration. And this is about understanding the workloads, being able to move application network function workloads onto the most appropriate server at that point in time. Through orchestration systems and to join all the bits together. So maybe it's multiple applications and their network connections and some storage links, all that lot, so that you can pick up workloads and move them to another center. So if, for example, you're running a production network, you might want to do some maintenance on a data center node, upgrade it or whatever, do some patches on it, picking up the workload, moving it somewhere else onto appropriate servers. This also gives you the ability to scale the amount of processing resource that's allocated to this workload in dynamically. So that if you see a traffic peak coming, you think, oh, it's coming up to the middle of the morning, traffic normally goes up, turning on more servers so to handle the production workloads. And then maybe in the evening, the traffic's going away overnight, you can shrink it down so that you're only using a small proportion of the available capacity, and you can turn the rest off, save some electricity, do maintenance, run other workloads. Now, that's where leading operators are. In 2017, that's the state of the art. The next stage on for them is looking at these network applications, because typically what we get today are proxy applications in the data plane where the go path and the return path go through the same piece of software, because the information that's carried in one direction has relevance in the opposite direction for things like the protocols. And what we're starting to see is people starting to understand that if they re-architected these sort of applications, that they'd be more compatible with classic cloud working as used in the IT space. So this is taking those proxy applications and saying, right, okay, how do I turn that into maybe a series of different transactions, a bit like, for example, a web server transaction? How do I do my network processing, that sort of transaction? The second piece is, because we're having very small, what are called microservices for this, we need to be able to distribute the traffic over multiple servers, and so there's a requirement for distributed load balancing, which is not as easy as it seems when you start looking at it in detail at it. And finally, because these applications are still stateful, there is a requirement for a database that has got a real-time database that allows you to synchronize things across multiple servers. So that's what we call cloud ready. And what we're expecting to happen is that we'll move from a cloud ready stage into a cloud native stage, and that'll probably be on in production in probably about 7 to 8 years. And at that stage, a telecoms operator would be able to have one platform that can run their network services, their cloud services, and their IT stuff all on the same platform. Okay, so what's inside NFV? This is a picture of the classic, what's called the ETSI NFV functional framework, which has three main pieces in it. The bit bottom left, the NFV infrastructure. So this is taking physical compute resources, storage resources, network resources, virtualizing all that lot so that you can get a virtual compute facility, you can get a virtual storage facility, you can get virtual network links, and they're all coming out of this NFVI platform, and they can make those resources available to virtualized network functions. So, for example, the VNF, the virtualized network function, might be a firewall, and it says, okay, this is the amount of processing I need from the infrastructure layer, and I need input pipes and output pipes, and I also need a management pipe as well to go off to my management systems. And those requirements for the VNF are handled by this thing at the right-hand side, the NFV Management and Orchestration, which is known as MANO in the industry, which understands precisely what the resource requirements are for that VNF to deliver the required network services. That's what that does. Okay. So, key NFV use cases. Where we are right now is that been going through a period over probably the last 3 or 4 years where people have been trying to understand operationally what this stuff's good for. And the first one of the first leading applications is what's called Enterprise Network VCPE. So this is again typically in fixed line operators who are providing services to enterprises where you may have a series of branches trying to connect to a regional or a global data center. And so on those branch sites, typically you might have a router, a firewall, a WAN accelerator, you might have a file server, and historically you would buy each of these things as a box and wire them all together. And where we've moved to is a situation where you can have a very small server sitting in the branch that can run these sort of applications and more things. So for example, operationally, you might want to have a service assurance monitor probe running in that thing as well, so you know precisely what the end user experience looks like. What's also happening is that telcos are starting to understand that they've already got a box out there, which is the network terminating equipment. When you provide an access circuit, typically there's a network terminating equipment, an NTE, on the end of it, acting as a demarcation point, and that that needs a bit of software on it. Okay, so these applications can be cited in a branch, could be cited in the enterprise data center, or could also be cited in the telecom operator's local node at the other end of the access circuit. So there's a number of different approaches. What we're seeing in the market is that the most predominant thing in North America is small servers at the branch site. Okay. The second area, typically in the mobile wireless network, is looking at the evolved packet core. So the packet core area is where we get this GI LAN space, where there's all these different services that you might want to introduce. And typically what people have been trying out here is machine-to-machine working and Internet of Things pilot projects so that they can set these up in parallel to the production voice and mobile broadband services and can learn about this sort of technology. So what we're seeing here, the key NFV use cases at the moment, are typically low risk. You know, nobody's going to get shot if one of these things falls over. In the enterprise network VCPE case, there's a quick fallback using physical boxes. In the evolved packet core stuff, it's very small amounts of traffic and it's pilot trials. And as people gain operational experience with this stuff, we're now seeing leading telcos start to run these things as full-blown production services with significant amounts of mission-critical traffic on them, having got that operational experience. And one of the other features of these sort of use cases is that you can get started with virtualization. You can put some workloads on a server. You don't need to have the clever orchestration and moving things around to get started. So this is about building understanding of what's going on. Okay, so what is going on? A lot of things are going on. A lot of things are going on in the open source space. And this diagram is from the Linux Foundation. The Linux Foundation, as you'd expect, are the people that cause Linux to happen. And Linux is the stuff down here, the penguin down here. However, there's a wide range of other activities going on round about that. So underneath the Linux operating system, we get things like the Open vSwitch, the ability to connect various virtual machines to one another. And there's projects like the Fast Data Plane IO initiative and the Data Plane Development Kit initiatives, which are about accelerating the performance of the data plane. Up here, Open Daylight is an SDN controller. North of that, we have OpenStack, the open source IT management stack that's been modified to handle NFV applications, and things like open source Mano. This is an orchestration system. Alongside this is a project called ONAP. ONAP has a number of PCs inside it. It's got an orchestration system which comes from a project called OpenO, and it also has a complete management stack, but both the resource level and the services level, which came out of an AT&T Domain 2.0 initiative, a thing called eComp. So that's a complete stack of software there. Also, alongside this, there's a project called OPNFV, which is important. What OPNFV is doing is joining all this lot together, and we'll show you more about that. Okay, so on the left-hand side here, we've got a load of things that are going on for the network stuff. On the right-hand side here, there are some pieces about what's happening in the IT cloud stuff. You'll see the boxes that have got solid lines around about them. These are Linux Foundation initiatives, which they're in the process of aligning, but there's a few others knocking around which are being operated by other standards groups. For example, OpenStack are running their initiatives. Okay, so and we're getting standards pulled together from various people, and the standards bodies are starting to understand that the way you do standards these days is probably by creating some software, trying it there, and then moving on from there. Okay, so this is OPNFV. What it does, the Open Platform for NFV, is it takes these compute, storage, network pieces of open source, the infrastructure, and makes that available to the industry on a 6-monthly cadence. So they're doing integration, they're doing testing, they're bringing new features in, there's continuous integration technology in here, there's lots of documentation and security initiatives, and this is supplied to the back end of the industry, so into the equipment vendors, but you can download this stuff yourself if you want to play with it, and it gives you a complete working stack. Not only that, there is an industry-wide global approach about how you test this stuff, so you can set up a test lab to emulate the results that are being done by any of the other significant players in this market. Okay, it's all there. Right, so that's what OPNFV is about. We've talked a bit about Cloud Ready NFV, so I'll skip over that. Okay. Then, what does all this lot add up to? What are the expected business benefits? Okay, there's 4 really. Firstly, what happened initially was people said, this is about cost reduction. And there certainly are some cost reduction opportunities. Because we've separated the hardware from the software and made them into work, you can start undertaking competitive procurement, both for the hardware and the software. Also, when you're starting to develop new services, the stuff is reusable. We've got virtualized servers here. You can put more workloads on there up until the loadings. If you discover that the market for one service has faded, you can use the same stuff for another service. We've got virtualized shared platforms. And the other thing that's key in here is the concept of Moore's Law performance evolution, where because of the rate of development of the silicon technology, you get a significant increase in performance every sort of 18 months. So that, looking at, how your traffic handling capacity needs to expand, say in a central office, you can quite often get away by just swapping out processors that are, say, 5 years old with new ones, and you'll get all the performance benefits you need without changing any of the hardware or any of the power supplies. The chassis hardware, that is, just changing the processors. Okay. However, so that was, if you like, a sort of CapEx story. Also, from an OpEx story, we're using standard hardware. Standard hardware is available all over the planet. There are stocks of this because it's supporting the IT industry. You can get this stuff, off the shelf anywhere. Okay. The second point, revenue growth from timely new service introduction. The difference about this stuff compared to the old way of working was that typically what would happen was that if a telco said, right, I would like a box that does this, an equipment manufacturer would get that into their development plans. Eventually they'd go away and develop it, they'd harden it, they'd make it all beautiful, and then say, there you are, there's a box that does what you asked. Whereas probably what we need in the market these days is the ability to do a very fast market trial, saying, I've seen this stuff, it looks good, let's try it out with some customers. Okay, do a more Google-like approach for new services, try something out. If it works in the market, go away and then do the hardening. Okay, if it doesn't work in the market, forget it. Nail it. Fast fail. Try the next one. So what you get is true innovation. Try 10 things and pick the one that really works. Okay. Third thing that you get in here is improved business contingency resilience. We're talking about standard processors here, so that it's quite possible to build your disaster recovery backup or whatever using the old stuff. Maybe you got a lot of it, and you can evolve things. We're talking about 1 in N resilience models here. So for N production servers, you may only need one backup. And so you get quite a lot of improvement there compared to the sort of classic approaches in networks where you might have a production one and a standby one available at more than one site. So you might need effectively 4 times as much hardware than you actually need to handle 1 unit of production traffic. The final thing that we get here is consolidation of the IT and the networking platforms. Where this thing is heading is looking at your information technology workloads, your OSS, your BSS, your enterprise automation. All this lot is typically running on x86 servers these days. Your cloud workloads, your cloud services, again, are running on x86. And the networking workloads, now we're saying, hey, you can run them on x86 as well. So that we're starting to see this crossover between the sort of the IT world and the comms world. And probably what will happen as a result is that in the Network Operations Center, we'll see a significant growth of the number of people that understand how to do software coding. Okay. Typically, I was speaking to an operator last week, and they reckon it was going to change from about 10% of the staff in the NOC being code literate to probably about 80%. So these are the sorts of benefits that service providers are expecting. So you can add all that up. Faster, cheaper, better. Okay, that's what it's about. Okay, so in conclusion, what are we about? This is the Telecoms Academy. I've given you an insight into some of the work that we're doing in the NFV and SDN spaces. Let's go and